In this video, I want to describe to you a different type of network model, different network architecture, in particular one that's closer to how the brain might actually be working, but still related to a lot of the backprop stuff we've been learning so far. So I want to show you about predictive coding. The goal is to see how a real brain might implement backprop-like learning. So backprop is amazing. We've used it for all sorts of amazing things. But can a real brain do backprop? So let's talk about some of the constraints on a real physical brain. A real brain is constrained by physics and chemistry. It can't just do anything. It's actually a machine. Every neuron is, in essence, a machine. So what does that mean? One thing it means is that synaptic updates can only be based on local information. That means they can only use information in its, each neuron or each connection, each synapse can only use information in its local neighborhood to drive its changes, to change its state. It also, in a real brain, connection weights cannot be copied from other parts of the network. So let's look at let's look at some specifics here. On the left here, I have a backprop type of network. And you can see there are a bunch of layers, and you can imagine that there'll be some weights here. And we get some output y and some target t, and then we have some loss function L. So what we do is we take this loss function and we project back the gradients, right? And they go down layer by layer. And then we use those gradients to update our connection weights. So for example, we might say our weights become our old version of our weights minus some learning rate times the gradient of our loss with respect to those weights. So that's backprop. Now, what about biology? So here I have a network that's meant to be a little more biologically driven. So we've got a bunch of neurons, and I have this little symbol for a synapse. And let's say we've got this connection weight here. The weight of that particular synapse, of that presynaptic neuron connecting to the postsynaptic neuron, has some weight W. And you can see that each neuron affects its downstream neurons, and eventually we get some, you can imagine some node or some neuron here which has an activity level Y, and maybe we have some target value T that we want that neuron to have, and then there's a loss function. So it's similar in nature to the backprop, except when it comes to training this network, if this network, this biological network is to learn, it's got to connect, it's got to change its connection weights, but driven by this L. So this loss here and this weight here are far away from each other. So how could the error signal have an influence on the connection weight? Okay, so that's the problem that we're dealing with. There are some architectures that implement something like backprop, but they do it in a more biologically plausible way. So if we can come up with a learning rule that doesn't require us to copy weights across the network, for which we don't have to use information from far away in the network, if then somehow the information, the gradients can be delivered to where they need to be used, that type of network we call biologically plausible. Biologically plausible. Okay. There are some architectures that implement something like backprop, but in a biologically plausible way. So let's talk about predictive coding, or PC. In predictive coding, predictions or commands are sent one way through the network, and errors or deviations from those predictions or commands are sent in the other direction. So it's a bidirectional network. We have essentially feed-forward connections and feedback connections going simultaneously. So to give you an idea of the sort of prediction sort of commands versus errors and deviations, let me show you this example of military chain of command. So in the military, I don't know much about the military, so I'm just kind of guessing here. But if you'll humor me for a few minutes, there's the general, who is the person in charge of everything. And the general has people underneath them helping them, so colonels and lieutenants. So they give commands to colonels and lieutenants, things like attack on the West Coast. So the general might tell the colonel, we're going to attack on the West Coast. It might tell the lieutenant, tighten border security. So these are very high-level commands that involve a whole infrastructure, a cascade of things that have to happen. So the colonel then, being told to that they need to organize an attack on the West Coast, will turn to people that they're in charge of and send sort of more detailed commands down to them. So for example, the colonel might tell the captain, move troops west. It might tell the major to stock ammunition. And then the captain, who's been asked to move troops west, might talk to soldiers, tell one soldier to drive a truck, tell another soldier to fly a plane, etc. So you can see how the different commands get broken down into smaller and smaller pieces, this sort of hierarchy. For the stock ammunition, the major might tell one of the soldiers to load a truck with ammunition, whatever. You get the idea. And same thing on this side with the lieutenant. There'd be a whole cascade of hierarchically sort of rendered commands. Now, let's say for each chain, or for each person in this web, in this tree, I guess, they receive a command and then they send sort of subcommands down the tree. And if they don't hear anything back, they assume that their requests are being fulfilled properly. Now, when something doesn't work for some reason, like let's say there's an ammunition shortage, so the major will report back to the colonel and report ammunition shortage. So there's not enough ammunition. So that's an example of a command being sent down in one direction and an error or deviation from that command being sent back up. And then so the colonel would then report to the general that there's a delay. So commands sent down, deviations from those commands are sent up. So this philosophy is called predictive coding, and it's fairly efficient because the commands basically flow in one direction, or the predictions are flow in one direction, and there's no need for information to flow in the other direction except when there's an exception. Except when there's an exception. If there's a command that cannot be fulfilled. So it's efficient in terms of the commands going in one direction, or the errors being sent up don't have to be encoded unless there's a delta that they need to report. So that's the idea behind predictive coding networks, is this forward and backwards flow of information, and one of the directions is only errors. So just to make a comparison here, we've got a feed-forward network. So you're used to seeing that sort of thing. Now the predictive coding network version of it is shown here on the right. Now you can see between any two nodes, there are two connections. So for example, between this node and this node, there are, or at least should be, two connections. You can see the one connection here. The other connection going backwards, I actually didn't make it. So there's a connection going backwards. So between any two nodes, there are two connections. In addition, we have sort of expanded each node into two pieces. So the hidden layer over here turns into this sort of double hidden layer here. So let me put some labels here. We'll call this x11. Or not. I'm not really going to use these labels too much. So you can see we have these layers are listed here. So this is the hidden layer, broken into sort of two different pieces. Now we have the predictions being sent up the network, and we have the errors being sent down the network. So in a PC network, each hidden node, don't even need the word hidden there. Each node is split into two parts. So what we have, whereas where we would have had a single node before, let me do it like this. Now we break it up into two pieces. There's this error part and this other part. And now we have communication between them, which I'll draw like that. Wiggly line. So usually when I put that little circle on the end of a connection, that means it's inhibitory or a negative connection. And the arrow means positive connection. The point here is that they have opposite signs, those two connections. Yeah. So now this epsilon here is an error node. And this X thing here is a state or value node. Just as a name. So each old node is now split up into, each old node becomes a single PC node which has two pieces, two subnodes in it, an error node and a value node. So what we'll do, just like we often do with neural networks, is we don't know how many nodes are going to be in each layer, so let's represent each layer as a single circle. And so here's a whole predictive coding network here. You can see there's input here, and up at the top here there's a target. And I've got a whole bunch of layers in between, and you can see I've grouped the error and state nodes together, but each circle here actually represents a whole layer, a whole population of neurons, and the error node represents another population of neurons that correspond one-to-one with the state nodes. So there's always a one-to-one correspondence of error nodes and state nodes within a predictive coding layer. Okay, so let's put some other labels here. First of all, we don't need this alpha here. That's for something else. Don't worry about it. Let's label these weights. This M1 is a weight matrix work going up the network, and W1 is the weight matrix going down. And so I can label them all the way up here. M n minus 1. I'm not using the brackets in the superscript. It just gets too busy. Now, each of these connections going up is a prediction. So I'm going to label that prediction as mu2 in that case. So it's the prediction being sent to layer 2. This is the prediction being sent to layer n minus 1. And this is a prediction being sent to layer n, the thing that's coming in here. And finally, this beta here controls whether or not there's input to this top node here. If we want to fix that top node at y, then we don't want to give any input. It'll just stay at the value y. So that beta value is a 0 or 1, and it controls the input to the output node. Okay, so now we can set an input and we can set a target. And if we set this beta, oops, no, I want that. If we set this beta to 0, then this top node and this x here will stay fixed, and we can run this network, and those two sort of boundary conditions are going to influence the states of things in between. So we'll get to that in a minute, but just to finish labeling here. So mu superscript I is the prediction being sent up to layer I. And that's coming from layer I minus 1. These layers are in order. And in particular, mu I is equal to, I'm going to use row vectors again. It's the state of the node below it. So let's focus on one here. Let's focus on this one right here. So it's basically sigma of the state below it. These x's are essentially the input currents. So in that sense, this is a current-based model, and you have to run that current through an activation function before you can pass it on. So the activation function gets applied as you output from that node. At least they do along those connections between layers. I minus 1. So coming from the layer below times the connection weight matrix from below. And if you want, you can also add a bias, but I don't always, and I won't include it here. So for now, we're going to assume that the M and the W of a given layer are just transposes of each other. So the weights going up the network, you just transpose that to go down the network. Now this breaks the rule of copying weights, but you'll see that that the learning rule that we use to learn M and W, it's the same learning rule, and it does use local information. But for now, assume those are transposes. So assume Wi is Mi transpose. Okay. Now the error node, epsilon I, is the difference between xi and mu I. So remember, mu I is the prediction being sent to layer I, but layer I already has a state, xi, or a value. So epsilon I is basically the difference between the actual state and the prediction being sent. So error I is xi minus mu I over this sort of eta I believe that's an eta. I'll call it eta, which is just a constant. I won't talk much about that, but it's basically, it can sort of scale things according to how much noise you expect there to be in the error between the prediction and the actual value. So let's call this equation 1. Now I'm going to turn that into a differential equation for which that is the equilibrium solution. So some time constant tau times d epsilon 1 by dt is xi minus mu I minus eta I epsilon I. So at equilibrium, we get 1. So if you take that differential equation, run it to equilibrium, you'll see that 1 is the equilibrium solution. Epsilon equals xi minus mu I over eta I. So that differential equation is the differential equation, one of the differential equations that governs this model. And you can sort of see the connections. You can see that there are kind of different things coming in. One thing that's coming in is this xi. So if you look at, do I have okay. If you look at what's coming input, it's so here for epsilon 2, for example, what's coming in? Well, one thing that's coming in is input from the x in the same layer. So that explains that first x there. Now this mu, that's the thing input coming from the layer below. And then we just have this other decay term, which is part of the dynamics, but is not illustrated in that little drawing I have there. Okay. So the goal for training the predictive coding network is basically, given some input, we want to predict the output, right? So written down in a more detailed fashion, given a data set x, y, and set of connection weights and biases mi, wi, I equals 1 up to little n layers. What we want to do is maximize over the model parameters the probability of outputting x when our input was, our output y when our input was x. And I'll write it like that. And you can also say it's the probability of jointly observing the input-output pair and the set of connection weights. So writing this out, since it's in layers, we can actually turn it into a Bayesian chain. The first thing I'm going to do is say it's the probability of y based on the x given the parameters times the prior probability of the parameters. Now I have a whole research project into those prior probabilities, but we're not going to go there. Instead, we're going to focus on the first part here. So this probability of the output y, given the input, you can actually say given the input x and the set of parameters, can be written as a Bayesian chain. So probability of the output given the prediction sent to the output layer times the probability of the state node in the layer below given the input to its layer, and so on. So each layer basically has has an actual state and has a prediction being sent up. And so we can break this probability up into a bunch of chains, and basically asking to maximize the probability of the state of each node given the prediction being sent up. So we want the predictions and the states to match, essentially. x2 given mu2, and then times the prior probability of theta. But like I said, we're not going to deal with that too much. Okay, now consider one link in the chain. Before I go into more detail there, let me give you a quick joke. I couldn't figure out why the baseball kept getting larger. Then it hit me. Okay, so looking at this one chain, this one piece in this chain, we're going to assume that xi is Gaussian distributed around mu I. Assume xi is normally distributed around mu I with standard deviation eta I. Normally distributed. Okay, the nice thing about that is we can take the log of it and then we get this nice thing coming out. So that we'll get there. Therefore, the probability of xi given mu I is 1 over something. This is just a Gaussian function now. E to the minus xi minus mu I squared over 2 eta I. Now taking the negative log of that, gives us some constant plus 1 over 2 eta I times xi minus mu I. So you've probably seen this a number of times, right? It's taking Gaussian log of it turns it into basically squared error situation. So that's just for one layer. If we were to take the negative log of this whole thing, then we get the sum over all of those layers. So therefore, negative ln of py x theta is basically proportional to, I guess, or minimizing that is the same as minimizing this. I equals 1 to n xi minus mu I squared over 2 eta I. So this kind of leads us to a Hopfield function. Let's define f as basically that function up there. I equals 1 to n of eta I over 2 times epsilon I squared. Because you see that this thing inside here is basically what it's almost exactly what I defined to be epsilon. Here's epsilon up here. So it's epsilon, except that I need to, there's like a factor of a half and there's a factor of eta as well in there. So recall that epsilon I is xi minus mu I over eta I. So this extra eta and over 2 and stuff are just to sort of make everything else work out. Okay, now if that's our Hopfield function, then like we've seen in other Hopfield functions, gradient descent on that Hopfield function is how we, it basically reflects the dynamics that we want our network to do, so that our network automatically tries to minimize its Hopfield function. So let's take the gradient of that Hopfield function with respect to xl. L just being some layer. So note that xl appears in two different terms. It appears in epsilon L, right, like here, but it's also in the mu. And remember, mu is sigma xi minus 1 times m I minus 1. So that the xl will appear in epsilon L plus 1. You could think about that. So epsilon L is 1 over eta L times xl minus mu L. Epsilon L plus 1 is 1 over eta L plus 1 xl plus 1 minus mu L plus 1. But the mu L plus 1 is, well, this is what I just wrote up there. So here's our xl and here's our xl. Therefore, the gradient of f with respect to xl is the sum of those two parts. So the gradient, first of all, this one here is just 1 over, oh no, sorry. So our f is these epsilon squared. I won't go into the details, but you can verify it pretty easily. The first term will give us epsilon L, because each term is a quadratic in epsilon L. So when you take the derivative, you get the 2 comes down, it cancels the other 2, yada yada. And the other term, which comes from here, looks like this: sigma primed xl times, let me do it this way, epsilon L plus 1 times ml transpose. Okay, thus gradient descent of our Hopfield function, the dynamics the gradient descent will have on XL gives us this differential equation. Again, some time constant times the rate of change of XL. So this is implementing gradient descent in a continuous domain, continuous time domain. We get this. Now I'm using the fact that WL is the transpose of ML. Okay, so this is our second differential equation. I already gave you a differential equation that governed the epsilon error nodes. Now this is another differential equation that governs the dynamics of the state nodes or value nodes. This one's derived directly from the Hopfield function. And you can see its connection. So if we're looking at x, let's look at this x here. Each term corresponds to the connection. So this connection here coming from the epsilon, that's this thing here. This other one, this other connection is times w. So that's this other term. It's epsilon from the next layer up times the weight matrix. Now this is a thing that's kind of weird, is that you multiply by the derivative of the activation, the derivative of the activity of the state node. I find that weird and a bit uncomfortable, but that's just what the Hopfield function says we should do. Okay, so now we know how our error nodes are updated. We know how our state nodes are updated. How do we train this network? To train the network, you clamp the input on both ends. So for example, remember this alpha is not actually there. So you clamp the x and you set the y, and then you set beta equals 0. So when beta equals 0, that means xn will be fixed to the value y and won't change because there's no other input coming in, so it just stays put. There's no decay or anything. So you hold those inputs and run the network to equilibrium. So you hold the x and you hold the y and you let time go, and the network state's going to adjust itself until it doesn't change anymore. And that's equilibrium. So at equilibrium, all the derivatives are 0. So d epsilon L by dt equals dxL by dt equals 0. So here's kind of the secret to how the network gets around this idea that you can't move an error from one end of the network to the other, to this other connection where it's needed. If you run the network to equilibrium, that in essence gives every node a chance to interact with every other node, right? So information has to sort of permeate through the entire network before it can actually arrive at its steady state equilibrium state. So once you're at equilibrium, in effect, every node has interacted with every other node and they have reached this balance, this sort of global agreement. Okay. Now, so let's look at the fact that we have equilibrium in these different state nodes. So that means that tau dx, should I use I or L? I guess I'll use L. I'm just rewriting the differential equation. That has to be 0 at equilibrium. Oops. At equilibrium. So if that's true, then we can just look at this equation and solve it. So that tells us that epsilon L must be sigma primed XL times epsilon L plus 1 times WL. Or we can rewrite it as epsilon L equals sigma primed XL You write it this way. Okay. So at equilibrium, this is a relationship between the epsilon, the error node on one layer. It's a relationship with the error node on the layer above it. This error node up here. So here's where we have the link to Backprop. So this is the work of Raphael Bogatz, someone that I met while on sabbatical at the University of Bristol, but now he's at Oxford. So let's start with the top gradient. I'm going to show you how that's, well, you maybe already recognize that that formula that I wrote for the epsilon, it looks like the Backprop formula. So if we start with the top gradient, remember we got a fixed y, this connection is not doing anything, but we do have this mu n coming up from the layer below. So this epsilon n is going to be the difference between the prediction and the actual state at the top, the target state that we want. Now if I were to take the gradient of my Hopfield function with respect to mu, with respect to that input current to the top layer, the prediction going to the top layer, remember epsilon n is xn minus mu n over eta n. So it doesn't look like that should be an x. So there's this minus sign here, so that'll explain where we get a minus sign. It only depends on this one term. So if you take the derivative of, or the gradient of epsilon n squared with respect to mu, and you get, put all together and simplify, believe it or not, it just turns into negative epsilon n. So the gradient of our Hopfield function with respect to the prediction going into the top layer is just negative the value of the error node. So that error node at the top is telling us our gradient. And it gets set automatically. It's just part of the network dynamics. But we also derive that at equilibrium, now this is a formula I wrote just above, epsilon L is sigma primed XL times epsilon L plus 1 times ML transpose. Now, if you were to go back to week 3 and look at the Backprop lecture, I wrote something like this. The gradient with respect to the input current to layer L of the loss function is sigma primed of the derivative of the activation function times, and then we have the gradient here from the layer above times the weight matrix transpose. So these look very much the same. In fact, they pretty much do look the same if you allow that this is the gradient and we're passing that gradient down one layer. So negative epsilon L is the gradient of the output error. It's the gradient of the output error with respect to the prediction going into layer L. So this shows that gradient descent on that Hopfield function is equivalent to backpropagation. And the reason we can get that link is because we're running the network to equilibrium, which allows the gradients to permeate through the network. Another quick joke. A child's face can say it all, especially the mouth part of the face. Okay, now we have differential equations to update the error nodes and to update the state nodes, and I've shown you that that they have a link to the Hopfield function. The differential equation that updates the error nodes almost is, I haven't quite made that link. It'd be nice if it was also gradient descent of the Hopfield function. It's almost, but not quite. I'm not quite sure what to make of that. Skip it. So let's consider, what about gradient descent of the Hopfield function with respect to the connection weights and biases? Well, I'm not going to do biases, connection weights. So consider the gradient of the Hopfield function with respect to the connection weights ML. So I won't derive it here, but you could probably figure out how to get this formula. And likewise, the gradient of the Hopfield function with respect to W, the other weights going down, is exactly the same, just transposed. So this is why, assuming that the M and the W are transposes of each other is not just weight copying, because they can actually be learned independently to be essentially transposes of each other. Now, if we use those gradients for gradient descent to update our connection weights, then I could write down differential equations that govern the change or the dynamics of the different connection weight matrices. So different gamma, I'm going to use gamma as my time constant for this differential equation. dml by dt, so the rate of change of that weight matrix with respect to time, is going to be negative the gradient, right? So if we were to look at these, at what's going on here, we have the state node from one layer and the error node from the layer above it, and they're sending information back and forth through their connections. This is the ML, and this is the WL. Now, these formulas here, these differential equations, only use local information. The update to M uses only the presynaptic activity and the postsynaptic activity. So adjacent to a synapse, all it needs to know is where it's coming, the activity where it's coming from, the activity where it's going to. All that information should be available in the synapse or in the vicinity of the synapse. So in that sense, these update rules, even though they're, I'll show you that they're basically doing backprop, they are local rules, and so satisfy that biological plausibility constraint. Okay. Now, these weight update formulas are the same type of delta rule that's used in backprop. So again, from week 3, I wrote down a learning rule like this. Well, this is actually a gradient, but it's the same idea as the learning rule. I had this HL column vector times this gradient thing here, which is a row. So this was an outer product, just like we have up above. And moreover, this thing here is basically the activity from the layer below. So it's like the sigma XL, if you will. And this thing here is the gradient from the layer above. So it's like epsilon L plus 1. So our learning rules in these differential equations are basically mirroring the same thing as the backprop update rules. So the time constant for the weights, these gammas, the time constant for the weights, gamma, is larger than the time constant for the nodes, the error nodes and the value nodes or state nodes, tau. So that means the error nodes and value nodes update more quickly. This allows the value nodes and error nodes to converge to equilibrium faster. And so when they converge, they set up the pieces needed for the weight updates. So the epsilons and x's converge to their equilibrium quickly, and once they're at equilibrium, then the updates for these weight matrices can use those values and change the connection weights. So the whole system is basically 4 differential equations per layer. So I'll just write them out now. This is for L equals 1 up to n. Maybe L equals 2 up to n. I mean, maybe the input layer is not a full layer. You can sort of choose how you... Oh, it is a full layer, I think. Yeah, it's a full layer. Anyway, so all 4 of these DEs can be run simultaneously. It's not like you have to do feed forward pass and then you fix the node values and then you update the connection weights. If you run these all simultaneously, the fact that the x and the epsilon update faster will take care of the fact that the connection weights are updated based on the equilibrium values of x and epsilon. So all 4 differential equations can run simultaneously. Okay, so these are the dynamics that will automatically minimize that Hopfield function by gradient descent, and I've shown you that the sort of result of that is reducing the output error, making the output of the network match the target. So here's when you train it, remember when you train it, you set X and clamp it, and you set Y and clamp it, you fix those 2, and you run the network to equilibrium. As it runs to equilibrium, it's going to sort of, it's going to find like the minimum energy state that it can find, but probably at the very beginning, those error nodes are going to be registering the differences between the different layers, the representations in the different layers. But as time goes on, and the connection weights update, they're going to drive down those errors. And in the end, what you want, a trained network, when you fix the X and Y on both sides, when that network relaxes to equilibrium, those error nodes go to 0. And that epsilon equals 0 is part of the equilibrium solution. And when those epsilons are 0, then you have no more updates to your weights and biases, because epsilon is one of the things in your learning rule for your weights and biases. So after you trained it, if you want to test it, you clamp the X, but you don't clamp the Y. You don't set the top layer, you just fix the input layer and you run to equilibrium, and the output is going to converge to whatever it converges to. If you've trained it properly, it will converge to the output that you wanted, just like running a feed-forward network. In fact, you can show that the network state you get is equivalent to running a feed-forward network just using those M weight matrices. So in testing, you clamp the input X and run the network to equilibrium. Once at equilibrium, Xn, the state of the top layer, is the network's output. So here's a paper written by Whittington and Bogatz I mentioned before, just showing that over time on MNIST, it learns. So what we have here is the error. This here is the test error. Goes down to about 2% or something, which is standard. And the training error, just like any feed-forward method, can go very close to 0. Like it gets like 99.5% accuracy. So this is using a biologically plausible learning rule. Predictive coding is a way of interpreting backprop or implementing backprop in a network that only uses local update rules. the secret is, the reason this is possible is because we're running the network to equilibrium, which allows information to sort of permeate through the entire network. So the error gradients can be delivered by these feedback connections down through the network, and that's exactly what happens. This is not the only method that is like this, that is sort of a biologically plausible implementation of backprop. There are other methods, but the common theme that they have throughout them all is that you have to run the network to equilibrium. For each data sample, you have to run the network to equilibrium, which allows information to permeate through the entire network.